beginning, so I've prepared just a few slides just to introduce the workshop. So let me share the screen. Okay. Do you see the screen, right?
Yes.
Okay. So welcome everybody. Good morning. My name is Gianpaolo Cuozzo and I'm head of research at the National Laboratory of Wireless Communication of CNIT. And today we'll introduce the section and share the first part on behalf of Luca Sanguinetti, who is not able to join the meeting. So to start, just a brief overview of the history, in the sense that this is not the first edition of the workshop, since we have already done it in Bologna on February the 1st, 2024, so in our headquarters here. And you see some photos of the event. We had the same 3 projects involved at that time, but we had also a collaboration with Restart In, which is the one of the biggest projects of the National Recovery Resilience Plan of Italy, that of course is focused on the telecommunication part. Today is the second edition. We just have, as organizers, basically the 3 European projects. The first one is TIMES, which is focusing on mesh network for industrial networks working at terrace, where the PI is Luca Sanguinetti, as I said. And then the second project is CG Shine, which is focusing basically on the in-X paradigm, where the PI is Gilberto. And then the third project is TERRAMETA, which is focusing on RIS, and whose PI is Luis. But all these 3 projects belong to SNS Call 1, so the 2022 call stream B. And today the agenda is depicted in this slide, as you will see. And so this is the introductory part, and then there will be 3 main sections. The first section we refer to 2 speeches from the TIMES project. So the first one will be from Sara Cavallero, and he will be talking about MAC and routing protocol design for multi-op terrace networks. And then the second one will be from Guillaume, and it will be about measurements of IRS at 300 gigahertz. This is basically one fundamental work that we are doing in TIMES because we are preparing the proof of concept that will be showcasing this year. And then there will be the second section. Instead will be where the focus will be on the CG Shine project, and we will have an hardware focused talk regarding a power analysis study, and the speaker will be Meg Lee. And then there will be the break in between at 10:40, and then we will have another speech about signal processing aspects regarding MIMO detection from Frederick. And then the workshop will end with other 2 speeches from the TERRAMETA projects. One speech will be hardware-focused speech, and we will be talking about waveform control, and the speaker will be Antonio. And then there will be channel characterization beamforming design speech, so more signal processing aspects, and the speaker will be George. And then there will be we have also inserted the 10 minutes of final discussion that can be related to what we have heard or any other technical aspects that we would like to discuss about. So some final recommendations in order to have a smooth realization of the workshop. So for the speakers, I would like to remind the speakers that they have 30 minutes per speech. This means that they have to leave some spaces for some time for questions in these 30 minutes. So please be on time and allow a fruitful discussion about the topics that you will be presenting. And regarding the audience, is that during the presentation, please keep your microphone off And at the end of the presentation, if you have any question, please raise your hand to reserve a question so that the chair will be able to give floor for questions. So, as I said, the time section will be chaired by me. The CG section will be chaired by Gilbert, and the final section will be chaired by Sergio on behalf of Luis. So this was actually the general introductory presentation. So I think that if there are no questions, we can move to the first speaker. That, as I said, is Sara Cavallero. She's a researcher of our lab, YLab, and her research topic is about MAC and routing protocol. And so she will be describing what she's doing in the TIMES project. So please, Sara, the floor is yours.
Thank you. I'll share my screen. Okay. Can you see my screen?
Not in presentation mode, but yes, we see it.
Okay. I think that now you should see it in presentation mode.
Yes.
Okay, thank you. Okay, so good morning to everyone. My name is Sara Cavallero, and I'm a researcher at YLab. In particular, I am involved in the TIMES project, and I'm currently working on a task with the goal of providing a design of medium access control and routing protocols in multi-op TERRAMETA networks. This project focuses on an industrial Internet of Things scenario where there are industrial devices that are deployed within an environment. They collect data and they send the data collected in uplink through wireless links to a centralized control unit for the final elaboration. From the communication viewpoint, this scenario is extremely challenging. Density of devices and offered throughput might be extremely high. Controlling automation processes set very stringent requirements in terms of latency, and devices miniaturization is fundamental. For this reason, to fulfill such stringent requirements, the key wireless technology adopted in this project is the terahertz band in the frequency range from 0.1 to 10 terahertz. However, one of the major limitations of terahertz wireless networks is their restricted coverage range due to the very high path loss and susceptibility to obstacles. An option to overcome such limitations is the implementation of a multi-op communication, which could help in extending the coverage and ensure a reliable connectivity. Multi-op communication means that within the environment there are some intermediate devices that relay data from the source to the final destination. However, to manage the multi-op communication efficiently, it is necessary to properly design MAC and routing protocols, taking into account to all the peculiarities of the propagation at terahertz frequencies. And this is the main goal of this work. This is the outline of the presentation of today, so I will start describing you the system model implemented, then I will focus on the medium access control protocol considered and the two routing protocols that we have implemented for enabling multi-op communication. Then I will go into the details of the key performance indicators investigated, and I will show you some numerical results that we have obtained, and then I will conclude highlighting some lessons learned. Starting from the system model, the reference industrial IoT scenario considered is a factory that has been modeled as a parallelepiped, where there are n industrial devices that are called user equipments that are arranged in a grid-based layout. This grid-based arrangement ensures consistent spacing between the different user equipments, providing a controlled environment for analyzing the propagation condition. Moreover, this kind of layout is typical of industrial setup, where the assets are evenly distributed to optimize the workspace organization and accessibility. These user equipments collect data from the environment and send their data collected to a base station that is placed at the center of the grid. However, the communication is obstructed by the presence of obstacles that can be walls or metal objects. And we model these obstacles as cubes of fixed size, and we study their impact on the performance. So in particular, we focus on the uplink communication between the user equipment and the base station in a worst case scenario from the traffic point of view, which means that the buffers of the user equipment are always full, meaning that as soon as a user equipment has received an acknowledgement from the base station that confirms the successful reception of its data, it immediately generates a new data without any additional waiting phase. Note that propagation delays at such high frequencies are no more negligible because they can be equal or even larger than packet transmission time. If we consider an acknowledgement of 10 bytes transmitted with a bitrate of 30 gigabits per second, the acknowledgement transmission time is in the order of 2.6 nanosecond, and at a distance of 3 meters, the propagation delay is in the order of 10 nanoseconds. So it is larger and it cannot be neglected. So their impact on the final performance must be taken into account. Regarding the channel model, we have adopted one derived experimentally from Huawei within this project. In particular, through channel measurements, they were able to derive a characterization of the path loss, which depends on the path loss exponent and a zero mean Gaussian random variable with a given standard deviation sigma, whose values have been derived depending on the line of sight and non-line of sight condition between the transmitter and the receiver, and have been derived in the terahertz band. Then, knowing the characterization of the path loss, we were able to derive the value of the received power received from the useful signal. At the receiver side, to assess whether the signal has been successfully received or not, we evaluated the signal to interference plus noise ratio, defined as the ratio between the useful received power divided by the sum of the noise power and the sum of all the power coming from the interfering user equipments. In particular, we assume that there is a success if and only if the signal to interference plus noise ratio is greater or equal than a given threshold. So this is the system model that we have implemented. Now let's move to the medium access control protocol considered, that is an unslotted ALOA protocol. Why we choose the unslotted ALOA protocol? Because it is very simple and it is a distributed protocol, so it doesn't require any kind of centralized coordination between the different user equipments, and moreover it is unslotted, meaning that time is not organized into slots of fixed duration, and it doesn't require any kind of synchronization between them as needed in other MAC protocols, like for example time division multiple access. And this is an advantage because achieving synchronization at such a frequency is very complex, and so that's why we choose unslotted ALOA. Now, going into the details of this protocol, each user equipment starts in idle mode. Then, as soon as it has a data ready to be transmitted in the queue, it starts a random backoff phase in order to reduce the probability of collision. Moreover, the novelty that we have introduced for enabling multi-hop communication is that during the backoff phase, each user equipment is in reception mode, so it could receive data from other user equipments, and if the data is addressed to itself, then it becomes a relay for that user equipment. So at the end of the backoff phase, it transmits an acknowledgement to all the user equipment from which it has received some data. And then it starts a data transmission where it transmits all the data packet in its queue. After that, it enters in a wait-up state where it is in reception mode and it waits for receiving the acknowledgement that confirms the correct reception of all its data. During this phase, since it is in reception, it would also receive other data from other user equipment. And if it doesn't have any data, that data in its queue, then it will become the relay for that user equipment. At the end of the wake-up state, if it has received the acknowledgement, it could send the acknowledgement for the other user equipment if it has received some data. And then it goes back to the backoff phase if it has some data in the queue. Otherwise, it goes back to idle. On the contrary, if it hasn't received any acknowledgement during the wake-up state, the transmission was unsuccessful, and so it reattempts data transmission up to a maximum number of attempts. It is important to say that we are considering a system operating in half duplex mode, meaning that if a user equipment or a base station is in transmission state, it cannot receive anything, and vice versa. Now let's move to the routing protocols that we have implemented for enabling multi-op. In literature, there are a lot of studies about this kind of protocols. The most common categories of routing protocols are the tableless and the table-based ones. Tableless means that each device doesn't build any kind of routing table, but the most common routing schemes are the floating ones, where each device forwards a duplicate of its data to all the devices that are within its communication range, so that at least one of them could receive and forward its data. On the other hand, table-based means that each device builds its routing table to find a route to be followed to reach the final destination. Route discovery is performed through the exchange of control messages, and there are two kinds of table-based routing protocols. The reactive ones, if the route discovery is performed on demand, so as soon as a device has a data, or proactive protocols if the route discovery is performed periodically. However, in this work, we propose two routing protocols, a table-based and a table-based solutions that are fully distributed, so there is no centralized coordination, and moreover, they are based only on the user plane data transmission, so there is no exchange of control messages. The table-less solution that we have implemented follows a floating scheme, so each user equipment sends its data with a broadcast address. This leads to the broadcast storm problem and a high overhead of information over the channel, but it increases the probability that at least one user equipment can receive the data and forward the data. Regarding the table-based one, since the goal is to build a neighbor table, so a routing table, each user equipment after the backoff phase enters in a discovery phase where it sends its data with a broadcast address to find the neighbors. Then it enters in the wait-up state and it collects all the acknowledgement received from all the potential neighbors. If at the end of the wait-up state at least an acknowledgement is received, then the user equipment selects the next stop and sends its data with a unicast address. The neighbor table contains several information. It contains the number of acknowledgement and data received from any other user equipment and the base station. Then we add an additional information in the acknowledgement received, that is if the transmitter of the acknowledgement has the base station as neighbor. And then another information is the level of receipt power received from the acknowledgement and the data. So now the question is how to choose the next stop. Of course, if a user equipment has the base station as a neighbor, it will select the base station. On the contrary, if there are if the base station is not a neighbor, but there is a user equipment that sees the base station, then it will select that user equipment. In case it has two or more user equipment that has the base station as a neighbor, it will select the one from which it has received the highest number of acknowledgement. And in case of parity, it will select the one from which it has received the highest level of received power. Again, in case of parity, it will select randomly one among them, among that user equipment. It is important to say that each user equipment has to continuously update the neighbor table, and in case the number of consecutive unsuccessful transmission from a user equipment exceed a value that is the time to live, then the user equipment has to remove the neighbor from the table, and it has to start a new discovery phase to find a new neighbor. Now, going into the details of the key performance indicators that we have investigated, the first one is the network throughput, that is the number of information bit per second successfully received at the base station side. It depends on the data size, the number of data successfully received at the base station, and on the simulation time that represents our observation period. Then we have investigated also the average latency, that is the average time needed to complete with success a transmission of a single data. It depends on the number of user equipments because it is an average value. It depends on the number of data generated by a given user equipment and not discarded. And it is in function of the time interval from the generation of a given data from a given user equipment to the reception of the corresponding acknowledgement. Now, I'll show you some numerical results that we have obtained. First of all, we have built a customized network simulator that works at 300 gigahertz. That is the carrier frequency that we have adopted in the project. It works and we have a bitrate in the order of 30 gigabits per second. We are considering a static scenario, so everything occupy a fixed position, and we are in a condition where in each simulation we have 1/3 of the user equipment that are directly connected to the base station, 1/3 of them that are connected to the base station via 2 hops, and 1/3 of them that are connected via 3 hops to the base station. The first numerical result that we have obtained is the network throughput as a function of the number of user equipment for the tableless protocol, comparing it with the table-based solution, considering a time to live equal to 3 and a time to live equal to 12. As you can see, the network throughput increases reaching maximum values and then it starts decreasing because as the number of user equipment increases within the network, there is a higher overhead of information over the channel, which leads to a higher number of collisions, and so the success decreases. What you can observe is that if the number of user equipment is 6 or 12, the table-based solution always outperforms the table-less one, thanks to the more reliable communication due to the next hop selection. On the other hand, as long as the number of user equipment increases, we can observe that the table-less solution outperforms the table-based one with a time to live equal to 3, because here the overhead over the channel is higher, so with a time to live so small, there is a frequent rediscovery of the neighbors, and this rediscovery could lead to a suboptimal next hop selection. On the other hand, the table-less solution with its broadcast data transmission increases the probability that at least one user equipment can receive the data and forward it. At such a frequency, the problem is the channel, because we have that with a number of interference equal to 2, there is a data loss. And so here it is the problem, and we lose the advantage of table-based. On the other hand, considering a table-based solution with a time to live equal to 12, which is much higher, allow us to keep a more stable neighbor table, and so we avoid the instability introduced by the root rediscovery. Then we have evaluated the average latency as a function of the number of user equipment for the table-less and the table-based with time to live equal to 3 and 12. As you can see, as the number of user equipment increases, it increases the average latency because of the higher overhead and the consequent higher number of retransmission. As you can observe, the table-less solution is the one providing the worst performance in terms of latency. This is because even if the data successfully reaches the base station, maybe the route that the data follows is not the optimal one, and so it is not the shortest one. On the other hand, you can see the advantage of selecting the next stop and proceeding with a unicast transmission in table-based. And in particular, we can see the advantage of considering table-based with a time to live equal to 12. So from these results, we can conclude that the table-based solution is one that provides the better performance as long as we consider a high value of time to live. Then in this numerical result, we focus on a number of user equipment equal to 12, and we consider the table-based solution with a time to live equal to 12, and we compare it with the table-less solution. This graph shows the network throughput as a function of the payload size, varying the contention window size of the bake-off phase. What you can observe is that a higher contention window size leads to a better performance in terms of throughput, thanks to the greater time diversity between the user equipment, which would help in reducing the probability of collision. However, as long as the payload size increases, the network throughput reaches its maximum value and then starts decreasing because of the higher overhead of information over the channel. And then you can observe that as long as the payload size is higher, the table-less starts outperforming the table-based solution for the reason I said before, because when there is a high number of collision, it increases the need of performing route rediscovery, which could lead to a suboptimal next stop selection. So to conclude, what we have done in this work is to properly design an slotted ALOA MAC protocol and two routing protocols based on the user plane data transmission only for the route discovery. And in this way, we were able to enable multi-op at such high frequencies. Under static condition, we were able to achieve a network throughput in the order of few gigabit per second and an average latency lower than 2 microseconds in all the cases, which is a very promising result considering the requirements of industrial applications. And what we have learned from this work is that these results are highly scenario dependent. The channel is a problem at such high frequencies because the interference between more than two user equipment leads to a data loss. And as soon as the number of user equipment increases and also the payload increases, we have that the table-based solution loses its advantage over the table-less if a user equipment loses its neighbor. And then with a bitrate of 30 gigabits per second, we can achieve a network throughput that is lower than 3 gigabits per second, and this is due to the high number of collision and data loss. Then we have also studied the performance in a dynamic scenario where we move the user equipment and the obstacles within the environment, and we have observed a small variation in the performance, and this is very good because it is due to the fact that we have a fast reconfiguration of the neighbors table in the table-based solution because it takes few microseconds to find a new neighbor and rebuild its neighbor table. Just a a quick overview of other activities that in which we are involved as YLab group in this task. One is about the design of a multi-agent deep reinforcement learning table-based routing protocol for optimizing the selection of the contention window size and the buffer size depending on the traffic within the network. Then we are working on an AI-based MAC optimization for multi-goal scenarios. And there is also a more fee-oriented activity that is about the radar-based localization and risk-aided communication in industrial terahertz networks. And here, this concludes my presentation, and thank you.
Thank you, Sarah. Perfectly on time. So I would ask the audience if there are any questions. I cannot make questions because I'm directly involved in activities, so please be active.
Okay, maybe a question from me. This is Gilberto. Thanks, Sarah, for the nice presentation. I was actually a little bit wondering, maybe you mentioned and I missed it, but what makes these protocols, these solutions, let's say, particularly suited for terahertz communication? So can those be applied also to our lower frequencies and so on? Is there any specific aspect, if you can comment on this? Yeah.
Yes, they can also be applied to other frequency and also to other reference scenarios. So they can be they are not particularly thought for that kind of frequency. The point is that we have applied and we have designed these routing protocols accounting for the peculiarities of such high frequencies. So, for example, we are considering a MAC protocol that doesn't require any kind of synchronization because at such a frequencies is very difficult to be achieved. We account for the impact of the propagation delays and moreover, differently from what occurs in literature, we are considering a routing solution that doesn't require any exchange of control messaging for performing the route rediscovery, but they can be easily adapted to any kind of other frequencies.
Okay, I see. Thanks.
You're welcome.
Thank you, Gilberto. Are there any other questions or comments? Okay, it doesn't seem so. I would like to thank Sarah once again. And I would like to move then to the next speaker. That will be Guillaume from CMRS, once again from the Times project. So Guillaume, please, the floor is yours. I think we are not hearing you.
You hear me now?
Yes, now we hear you.
Okay, okay. And you should see the slide, right?
Yes, we see it.
Okay. So thank you for the introduction, Gianpaolo. So indeed, I will discuss about measurement of ERS at 300 GHz related to the work which is done in Times. So this is mainly some work which is done in the project where we are going to validate the use of this kind of devices in free space, RIS, at 300 GHz. So let's start with some general, let's say, description about what we want to do. So in Times, there is some, let's say, network level and also hardware and system level demonstration to validate the approaches and the scenario for use that in terahertz. And basically in the project, we are targeting to have two proof of concept of using terahertz hardware and a system level approach to validate the links for industrial case or industrial application. There is basically two proof of concepts that are targeted. So basically, each proof of concept is a combination of the use of end-to-end connection from network to a machine, which is provided by a modem that could be an FDD approach in POC1 and TDD approach in POC2. The terahertz link is itself composed of several subsystems. So as a starting point, obviously, we want to use some front-end modules, which are developed by our German colleagues using technology plus PLL and frequency synchronization and so on. We want to use obviously some terahertz antennas. So related to that, there is two POCs, so two different kind of approaches. The first POC will use mostly high gain antenna, and the second POC, which is targeting, let's say, reconfigurable links or links between a movable object. So that could be a robot, for example, and a fixed TX would be used with the low gain and steerable antenna. And obviously, in these POCs, we want to include some reflective intelligent surfaces, whatever it is fixed for POC1 and reconfigurable for POC2. In any case, the point to insert a RIS in the terahertz system is really required to characterize the RIS, which is in that case the goal of this presentation. So to go a bit further, the POC1 description in let's say overall description. Here you have the overview of the POC, which is containing basically two modems that are placed here in the two points within the tech lab partner. So the first modem is combined with the front end modules with high gain antenna to radiate the terahertz beam in a RIS, which is back reflecting to the receiver here, and the system is working in FDD. So it means that we have a duplex link between these two modems. So inserting the RIS in this kind of scenario would enable to have some non-line of sight communication between the two modems, because we want to communicate here at 300 gigahertz within a wall in the line of sight classical direction. So this is the first POC. And in the second POC, which is a bit more, let's say, challenging, we want to close the link budget and show some connection between one fixed transmitter side and one moving robot at receive side. To do that, we want to combine the use of the beam steering antenna to enable the reconfigurability of the link, and also to insert, let's say, a reconfigurable RIS to adjust the channel in real time. And again, this is quite challenging, but in any case, the key point between POC1 and POC2 is the ERS performance assessment. So related to that, let's start with the recap of the method that we are using to characterize the RIS. So these kind of surfaces can be of many folds. So let's start with a classical metal plate, which is here as a reference, which is a classical specularly reflected operating device on which the angular of departure is equal to the angular of arrival with, let's say, a beam which is not normally changed, especially if the roughness of the metal plate is good enough. Now, beyond this classical case, we have the reflective surface, which is operating in a non-specular case, on which the angular of departure is different from the angular of arrival, which is mostly what we want to discuss here in this presentation. And for the second POC, we have discussed about reconfigurable RIS, on which there is a kind of control of the surface, which is in that case, in order to be able to adjust the angular of departure as a function of angular of arrival. In any case, what we want to characterize here is the matrix between angular of arrival and angular of departure, and also the RIS losses, to be aware of the power penalty for the terahertz beam when being reflected on this kind of devices. So the characterization steps should end up with the determination of the operating frequency of the RIS, because in some cases, depending of the RIS approach, there is a frequency dependence of the RIS itself. So it's not let's say a frequency independent device, so it has to be characterized. As I said before, we have to characterize the angular behavior of the RIS, so identification of the outcoupled beams from the RIS. So it has to be known obviously as a function of angle, but also as a function of the frequencies. And at the end of the day, we want to categorize the RIS losses in dB, which is basically the difference between the non-specular, let's say, beam, which is reflected in the front side, and non-specularly reflected beam from the backside of the RIS or related to the metal plate if the RIS is not containing a reference metal plate. In our cases, the back plane of the RIS is a full wafer metallization. So we will use this back plane of the RIS as a kind of a reference to be able to compare the non-specularly reflected from the RIS front side and the specularly reflected from the RIS backside. So as I said before, the goal is to determine this angular of departure, angular of arrival matrix to be able then to refine the scenario of a use of the RIS and the integration of this RIS on the final POC1 or POC2 definition. So let's start now with the ERS description. So this RIS prototype is fabricated by Anteral, partner within the TIME project. So this is a fabrication which is done on a 4-inch wafer, including the ERS. So here the first prototype is composed of an array of patches that are used to have a kind of a phase evolution with frequency. Here you can use some simulation of the phase evolution with frequency, on which we can identify where the phase is changing with frequency, the expected frequency of operation of this RIS. So this is for the unit cell, and after that the unit cell is used many times in the wafer to have a full, let's say, coverage of the reflective surface. So from these devices we can anticipate some let's say angular of arrival, angular of the departure matrix, which is depending of the patch design. In that case, what we want to define is the let's say the difference between the angular of incidence, which is angular of arrival, and angular of departure, which is the output from the RIS. In that case, everything is normalized to the specular, let's say, behavior of the RIS, which is obviously as usual, where a situation where the angular of departure is equal to the angular of arrival. So related to the design, this first RIS prototype is designed to be with a frequency with the angular shift of 30 degrees between the angular of arrival and angular of departure related to the specular, let's say, case, as I said before, compared to the metal plate. Here you have some view of some of the devices with a full wafer metallization with patches, and here a kind of a zoom on the different patches, and here you can see the different sizes of the patches that are used here to have this phase evolution versus frequency. So in terms of design, what is expected from this RIS is a kind of a behavior where when we shine the RIS with let's say with an incident beam which is at a normal incidence, we have an angular shift of 30 degrees around 280 gigahertz. So obviously it depends a bit of the frequency, but the maximum basically let's say frequency response is obtained at this frequency. It should be confirmed afterwards using the measurement. Related to the measurement, now we want to characterize this RIS, and we have to shine the RIS with a known beam to be able to extract the output beam and also to assess the angular of arrival, angular of departure relationship. So two kind of setups can be used for that. The first kind of setup is a frequency domain, which is a free space VNA, and obviously a time domain system like channel sounding can also be used. In that case, we will use here the frequency domain method, which is composed of the VNA system, which is two VNA extenders here, port 1 and port 2, combined with two horn antenna that are used to shine the wrist with a known beam. In order to make sure that the beam is only shining the beam, the beam is processed with lenses to be able to shine only the active region of the beam and outcouple from the only shine region of the beam. In other words, to not be, let's say, disturbed by the surroundings of the beam or the mounting system or external metallic parts. So as this is done, what we want to see here is two things. First, we want to assess the frequencies that are, let's say, non-specularly reflected by the beam. And a good way to do that is to shine the beam, to shine the wrist with an incoming beam of angular of arrival and looking at what is ongoing from the wrist at the specularly, let's say, positioning. In that case, if the wrist is operating, part of the test signal will be absorbed by the wrist, and looking on the comparison between the reflected in specular case from the wrist related to the metal plate, what we should see is an absorption at the frequencies on which the wrist is operating. And this is basically what is observed here. I will describe it afterwards. But here you have in black the specular reflection from a metal plate, and in red, the reflection in a specular case from the wrist. And what is observed is that you have a huge absorption here on which the frequencies correspond to the design of the wrist, on which you have these phase relationships with frequency related to the array of patch design. And then the second step is to determine the angular of arrival, angular of departure relationship. And for that, the receiver is moved around a circle to vary the angular of departure, and the reflection from the wrist in the non-specular case is done. And obviously, what we should obtain is a maximum of a reflection for the angular on which the wrist design is done. So what we should see is that for 30-degree shift between angular of arrival and angular of departure, we should reach a kind of a maximum of S21. So for the specularly, let's say, absorption, this is a zoom on the result. So as mentioned before, there is a clearly defined absorption region where the wrist is an absorbing device when it is operated in specularly reflected mode. So the outcome of this is to define the frequencies where the wrist is really absorbing. So as can be seen here, as I said before, the wrist is not a frequency independent device, and the wrist is only operating at, let's say, non-specularly device in this region. So obviously, if the wrist is not characterized in this region, it's difficult to obtain the, let's say, the wrist effect. Then for the non-specular reflection, basically here, the receiver is moved. So the port 2 of the VNA, which is the receiver, is moved with different angle, and we determine the evolution of the S21 versus the received angle. And as can be seen here, for an optimum angle there, on which the difference between angular of arrival, angular of departure is optimized, the S21 is a maximum. And then we can determine the wrist losses, which is basically the power difference between the metal plate, specular reflected beam, and the wrist non-specular reflected beam at the optimum point of transmission. And this is basically what was done with this first wrist design. And we observe that we have a couple of dB difference between the specular behavior of the metal plate and the non-specular behavior of the wrist. So the next step is to be able to use the wrist within a communication system. And in that case, what we want to inject on wrist is a modulated signal and not a CW from the VNA. So in that case, as you can see here, there is a bandwidth from the wrist, which is, let's say, a couple of gigahertz around the maximum, let's say, best operating frequency. And then we inject a modulated signal with a known modulation format and baud rate, and try to get outcoupled from the risk a signal and to try to detect it. So this is done with the datacom setup, which is described here. I will not go into the all details, but the main thing is that we have a transmitter there which is able to produce a kind of a modulated signal at 300 GHz. This modulated signal at 300 GHz is directly sent to the RIS, and we use the reference receiver, which is in that case a down converter and a wideband scope detection, to be able to extract the modulation and the typical metrics from the modulation, like EVM, orbital rate, and then we compare the link between a classical metal plate and the link with a RIS. This is the typical result, on which here on the left you have the performance of the system with a QPSK at 10 gigabit per second at 300 GHz, and in black this is basically the specularly reflected signal from the metal plate, so classical, let's say classical mirror at 300 GHz, and in red the non-specularly reflected from the RIS, so non-line of sight transmission with the RIS. And as we can see, there is a power penalty between the two, obviously, because there is a power penalty between the metal plate and the RIS. But obviously, as the RIS frequency response is not fully smooth, the power penalty is a bit higher than the RIS losses at the optimum point. This is expected. So this was validated in QPSK and also in QAM16, validating the use of this RIS within a full, let's say, terahertz communication links. So if you are interested, you can have a look on this publication, which is now out as a kind of output of the TIMES project. So the second RIS is an optimized design of the array of patches. So following the same concept of from the first one. So the characterization method is more or less the same. So again, it's using a VNA, a two-port VNA at 300 GHz. So you can see here the port one of the VNA combined with a horn, which is shining the thing on the RIS. And here the second part of the VNA, which is mount on the rotation stage to be able to determine the angle of arrival, angle of departure relationship, and the RIS basically in between. So several measurement has been done. So what we want to see again is the specular reflection, the bandwidth, and also the non-specular reflection from the RIS. So here as some example, the specular absorption versus the angular of the transmitter. Here the bandwidth, and here also the 3 dB bandwidth, the full bandwidth of the RIS. So I will not go into the full details here, but this is for specular case. And then we want to see the specular absorption from the RIS. So again, in this improved RIS, you have here the reflection from the metal plate, which is the backside of the RIS, and again let's say the specular absorption from the RIS, on which you can clearly see the absorption region of this second prototype of the RIS. So related to the second prototype, as you can see, it has been improved from the first one, and the absorption is much higher than compared to the previous one. So we could anticipate from the second generation of a fixed RIS a reduced, let's say, absorption at the optimum frequency for non-specularly reflected beam. So this is for absorption. And then if we now move on related to the simulation, what is observed here is that this was the expected bandwidth from the design of the patches from our colleagues from Terra, and it was designed to be around 280. And as you can see here, where the phase relationship is really expected and linear related to the frequency, this is really where the operation of the RIS is obtained, validating the concept of this RIS to be a kind of absorber for some frequency in the specular case. Now let's come to the non-specular reflection. So here there is several curves here to show you the concept of the test of the RIS for different angular of arrival, different angular of the departure related to the different position of the RIS. And then if we really move on the best, let's say, case, we have here the specularly, let's say, absorption of the risk on which is corresponding directly to the maximum of non-specular reflection from the risk. And then all of this measurement is now able to determine the matrix of angular of arrival, angular of departure that could be further used for, let's say, channel model or ray tracing. Comparing the second risk to the first one, at the end of the day, the second risk has shown only a 1 dB difference between the non-specularly reflected beam from the risk as related to the metal plate. So obviously, as we have seen, we were expecting a lower losses from the design, and this is actually what is obtained, and only 1 dB different from this second risk at 280 gigahertz band. Now, to finish, so some graph on to really identify the difference between angular of arrival and angular of departure. Here you have an example of angular of arrival, which is 38 degree at 281 gigahertz. And here this is the maximum of the S21 versus the angle, which is the position of the receiver. And as can be seen, this is a specularly, let's say, reflected, and non-specularly reflected is higher as can be anticipated from the risk design. And this is actually what is obtained with a 30-degree shift between arrival and departure, validating again the concept. And here some other graph which has been validated for different carrier frequency and different, let's say, incoming angle, because we want at some point to check that the concept of the risk is also a bit, let's say, robust to the slight variation of angular of arrival, which is indeed the case. So as a conclusion, some measurement of reflective surface has been shown, and basically enables angular of arrival, angular of departure matrix determination, and also, which is one of the key points, the frequency dependent of the risk, that are basically some input for channel modeling and also some inputs for the ray tracing at 300 gigahertz. Obviously, there is some next steps related to the TIMES project, which is in that case the measurement of the second risk with modulated signals, and also to confirm the operation of this risk with complex modulated signals, but also the insertion of this risk within the full communication system, which is basically the target of the POX, as I described before. And also some of the next step of within the project is to validate also the concept of this, whatever of the concept of the risk for reconfigurability, but also the measurement of reconfigurable risk, and further the insertion of the reconfigurable risk within a real terrace communication system, which is basically one of the outcome of the POC2, as I said before. Thank you very much, and please feel free if you have any questions.
Thank you, Guillaume. Also, in this case, we are on time. So, please, I would like to ask for questions. Okay. It doesn't seem that there is no questions. So, yeah, I would like to thank you, Guillaume, for this speech. And then I would like to leave the floor to Gilberto to chair the next session about CG Shine project.
Yes, thank you, Giampaolo. So good morning, everyone. As Giampaolo said, my name is Gilberto Berardinelli from Aalborg University in Denmark, and I'm the coordinator of the 6G Shine projects. I have the pleasure of introducing the next two talks of the 6G Shine projects related to hardware modeling, physical layer, but also signal processing. So the first talk is by Meng Li from IMEC. And the title of the talk is Sub-terahertz Transceiver Architecture Power Analysis for XR Indoor Gaming Scenario. So Meng, I'd like to leave the floor to you. We can see your slides, but we cannot hear you.
Can you hear me now?
Yes. Can you put the slides in
good.
presentation mode? Yes.
Let me see.
Great. So the floor is yours.
Okay, we are here. Okay. Hello, I'm Mandy. I'm coming from AMEC, and today I'm going to present our work carried out in the 6G Shine project for the sub-terahertz transceiver architecture power analysis for XR indoor gaming scenario. Here, I want to just take 1 minute to give a short introduction about the 6G Shine project. The 6G Shine project aiming to, at a pioneering the main technology components for wireless in X subnetwork and prepare their adoptions in the future 6G standards. The in-X subnetworks are located at the very end of the 6G network to support highly localized and high performance connectivity. In this work, we do the sub-terahertz transceiver architecture power analysis for the XR indoor gaming scenarios. The sub-terahertz, I want to have my, yes, okay, good. The sub-terahertz frequency provided a large bandwidth, which allows for the support for ultra-high throughput data rate. However, the PAs at these frequencies is not able to provide sufficient powers. And this is a problem, but since the wavelength of in the sub-terahertz is becoming associated with sub-terahertz frequency is smaller than the other frequencies, then it enables to use large antenna arrays and beamforming architectures to increase the link budget to ensure a high data rate transmissions in a small short distance. And my work will covers from 3 different aspects, from the device level, PA power model levels, and the system application. So I will first start with our studies for at the device level. So these figures listed the Fmax and Ft values for the state-of-art devices published in the literatures for different technologies. The Fmax means the frequency where the utilitarian gain becomes the unit, and Ft is the transition frequency where the current gain goes to unit. Both this Ft and Fmax are the figure of merits that is two important figure of merits for the devices in different semiconductor technologies, mainly used for the high RF technologies. According to the sum of design rules, for the operation frequencies of our PA need to follow the rules, some of rules, like it need to be smaller than the 5 times of Fmax, and the operation frequency of the PA need to be smaller than 3 times of Ft. So by this rule, and also if we look at the Ft and Fmax values of different devices, and then we can observe that the suitable technologies for the sub-terahertz frequencies fall into these rectangulars. which the operation frequency of the PA will be larger than 140. And then we can see, so there's device, the infosfy Hamet, the infosfy habit, and the gas Hamet, and the CG. Those type of devices are suitable devices for PA designs at sub-terahertz frequencies. And then let's look at the PA models, PA power models at sub-terahertz at sub-terahertz frequency. And so these figures, these figures plot the power added efficiency and the P set of the PAs, of different PAs, and the PAs are based of the state-of-art PA designs, and all those data samples fall into these figures are based on the latest PA survey published in the August last year, and based on those PA samples, we try to plot the trend of this PAE versus PSET, and the way we follow, we plotted this trend, followed by this, inspired from these PA survey figures, and we assume the PAE values will keep constant till a certain point, and then the PAs cannot keep the fixed PAE values, and the PAE values will drop at a fixed rate till the zeros, and to determine the shape or trends of these trends, this point can determine the shape of the trend, and this corner point is determined by two values. One is determined by the statistics values of this PAE and PSET, and here we plotted. Here, these tables listed all the numbers of this sample point of the different PAs with different technology node, and it listed the mean of the PAE for each technology node and the variation of this PAE. And it also listed the mean of the PSET and the variation of PSET. And we decided to plot the trend. We decide this corner point by the mean of PSET plus 1 standard deviation and the mean of PAE plus 1 standard deviation. And then we plot this trend, and this trend will be used as a power model for the PAs in the sub-terahertz frequency. And after we talk about the device and PA power models, then we move to the system application. In our study, we choose the indoor VR gaming scenario. The sub-terahertz link is a good candidate for the in-X subnetwork with short range and ultra-high speed requirement. When operating at the sub-terahertz frequency, power efficiency is a key concern, and hence so in this presentation, we're going to analyze the power energy efficiency for the sub-terahertz system for indoor XR gaming application. The VR systems are power hungry especially for the head-mounted device with external battery. So it is crucial to make power efficient design choice when building a VR system. We want to study the power model of our VR system using sub-terahertz communication and choose the proper system parameters as the bandwidth, the number of transceiver the number of antennas at the TX side and the number of antennas at RX sides that can minimize the power consumed for different VR realizations. Now we will give a brief introduction about the system models. So the systems includes the access point and two receiver, which I assume the receiver is for at the head-mounted device. And we note the number of NT is as the number of antennas at TX side, and NR is numbers of antennas at the receiver side. The transmitted signal from the access point can be formulated as this. So S is the transmitted symbol, and F is the MIMO precoders. And the signals received at the head-mounted device can be formulated as this. So this part is for the signals we design the symbols, and this part is the signals coming from the other users, and N is the noise. And the received scenic after the at the receiver K can be formulated as this. The throughput of the systems the required throughput at the system can be formulated with this equation. So the B stands for the bandwidth, and this part means the spectrum efficiency for a given scenic for a given user. So our goal and this part is and this spectrum efficiency is determined by the simulation, and it will be based on the MCS tables for our required performance requirement. And in our study, the required performance is target bit error rate at 10-5. And our goal is to find the TX and RX configuration that achieves required throughput and consumes the least power consumption. And so now the objective of our optimization problem can be written in this equation. Okay, is my okay. Can be written in this equation. So the PRX average means the average power consumptions at the receiver side, and the PTX average is the average power consumption at the TX side, and the PREF is the weighting factors which balancing the receiver and the transmitter powers. Our objective functions can be written as this. So we want to we sweep the different optimum. We find proper parameters in terms of the bandwidth, number of antennas for transmitter side and receiver side to minimize the weighted sum of power consumption by the TX side and RX side. And with the constraint that the throughput will meet the throughput requirement for different VR realization. Here we're introducing a factor beta, which can tune our optimization objective. When the beta equals to 1, then it is only optimized we only optimize the powers at the receiver side when the beta equals to 0, and then our object is to only optimize the powers at TX, and we can also choose beta as different values. When it is set as 0.5, then we optimize the total VR systems, including both the TX and RX power. We solve our optimization problems by simulation with different channel realizations and system configurations, and the PRX average and the PTX averages are obtained by the power modeling tools for the sub-terahertz communication. So as I mentioned, in order to get the PRX and PTX average, we use our power model tools. So the power model tools consist of 4 different main components. So first is the PA, second is the analog front end. The third is the digital baseband, and the fourth is the power supply. So for the PA component, we consider about the PAE and consider about the back-off point. And for the analog front end, it can model different analog front end architectures, and for each analog component, we get its power consumptions by chip measurement and also by simulations, including the DAC, ADC, LO, phase array, PL, and extras. For digital baseband, the digital baseband processings, including the major baseband functions like encoding, mapping, precoding, FFT and IFT, and filters and extras. And we models the complexities of each digital functions, and we model these complexities in GNOPS, and then we calculate the powers by this GNOPS per watt based on different technology node. And I will skip for the power supply because in the following result, this power supply is ignored. And let me introduce the system parameters. So we abstract our problems like we have the access point and the 2 head-mounted device. So these tables listed the system parameters. The frequency is fixed at the communication frequency is at 140 gigahertz, and then we can swap between different bandwidths from 1 to 2 till 16 gigahertz, and we assume the output powers at the PA is 15 dBm, and we have different options for the number of antennas for TX. So it is starting from the 48 till 128. And the number of users it's fixed at 2. And the numbers of the antennas at the arc side is fixed at 1, 4, 8, 16. And we assume the TX, we assume the access point, we assume the distance between this indoor gaming area is user distance is unitary distribute and between 0 to 5 meters, and the access point height is at 5, and the user height is unitary distributed from 1.5 to 1.8 meters. The noise figures for LN is 5 dB, and we simulated with 500 different channel realization. And in our study, we first just focus for this. We choose fully digital beamforming architectures, and the technology node for the digital circuits is choose at 28 nanometers. And with this system parameters, and then we study the impact of system bandwidth and the impact of the number of TX and RX antennas, how these parameters impact on the overall VR, the power consumption of this VR system, and with different VR realizations, which were impacted by the video resolution and the codec compression rate. And the optimization goal is for the 3 different cases. We only optimize the powers at access point and only optimize the power at head-mounted device and optimize the whole systems. As I mentioned in our study, we only for the simplicity, we just focus on the fully beamforming architectures, and these figures just show you the power models and the architectures, the analog power models of this analog component and the digital beam and the architectures for the digital baseband for TX and RX. And our and the power numbers for this digital the power numbers for the analog front end is the power numbers of each element of the analog front end is getting from the chip measurement from this millimeter wave chips, and it's published in the ISCC. And some are from the simulation. Some elements are from this chip measurement, and some probably from the simulation. And then let's look at our results. So first, as I mentioned, for different channel realization, for different video quality and different codec compression rate, well, leads to different throughput requirement. And in these studies, we studied the state-of-art 4K quality video 4K video quality, and for the future for the 8K video quality. And since we are thinking about the sub-terahertz communication, so we're targeting for this, we focus on the uncompression rate, which for the 4K VR scenarios, the target throughput is 10.6 gigahertz per second. And for the, if we move for the next phase of this VR systems, the target throughut is 63.7 gigabit per second. If we introduce some codec and with the codec rate compression rate 5.1, then the target throughput for this 4K case, 4K video quality case, the target throughput is 2.12 gigabit per second, and for 8K is 12.7.4 gigabit per second. And now let's look at our simulation results. So those figures shows the number of antennas at TX site versus the average throughput per users for at a different bandwidths and for different for different RX antenna numbers. So for number of antennas at the receiver side for 1, 4, 8, and 16. Here we listed the throughput requirement for the 4K uncompression codec rate and 4K VR case for this ultra low latency compression rate with the codec rate 5:1. And for all the points which above the throughput requirement are the other configurations, system configurations meet the throughput requirement. And that will be taken into account for this power co-optimization later. And in general, we can see the throughput scales with both bandwidth and antenna array size. Now let's look at the power results. And these figures shows the average power numbers at TX and RX for this 4K VRK quality 4K video quality with uncompression codec rate and 5.1 compression point rate. And then let's look at if we only let's take our optimization goal with beta equals to 1, and in this case we try to find the optimal system parameters with the least powers at the receiver side, and then we the point is here. The yellow one. So in these configurations, the bandwidth is with 4 gigahertz, and we have one antennas at the receiver side, but we have like 128 number of antennas at the TX side, which leads to a very which leads to the power consumption at the receiver side only to 0.71 watt, but at the receiver at the transmitter side, the powers will go up till to 38.6 watt. And then let's look at if we take our optimization goal is to optimize the powers at the transmitter side. Then we can find the optimal system parameters configurations is at this point. And in this case, in this case, at the receiver side, the number of antenna is 16, and the transmitter side, the number of antenna is 8, and with 8 gigahertz band. In this case, we can say if the powers at the transmitter side is 4.7 watt, but at the receiver side, the powers will go up to 8 watt. And of course, if we want to say want to optimize optimize the VR systems as total, then we can find the optimum parameters is 4 at this range, and I will not go into detail of these numbers. And then we can, here is the figures which shows the power breakdown for the 3 optimum case for 3 different optimum optimization goal for the optimum system configurations with the minimum powers at the transmitter side, at the receiver side, and for the whole system. And we can say once we want to target the least powers burned at the receiver side. The power spent at the transmitter side is quite high, and since the baseband consumes the most power consumption, this is mainly because we choose the fully digital architectures and a lot of complexities for at the baseband side. But the main message is by offloading the powers from the receiver side, offloading the powers from receiver side to the transmitter side, we can really reduce the burden at the power burdens at the head-mounted device. Okay, now I'm going to conclude my work. So based on the latest PA survey, the parameters of D-band PA models are updated for the InfoSphy, CMOS, CG, and respectively. We extended the power models for VR systems by accounting for both access point and head-mounted device power consumption in sub-terahertz multi-user MIMO scenarios. A joint optimization problem was formulated to minimize the total power consumption of the access point and head-mount device, either joint or individually, while satisfying the throughput requirement of VR applications. We explore the trade-off between the complexity of the access point and head-mount device, offering insights into system-level design choices for various VR user experience, considering different video resolutions, compression schemes, antenna configurations, and the bandwidth settings. We investigated how shifting computational power impacted the overall system power efficiency, especially for the battery-constrained head-mounted device. Here are the references, and thanks. That's the end of my presentation. And if you have any questions, so welcome.
Thank you, Meng. So any comment or question to Meng?
Yeah, well.
Seems no. Maybe just a very quick, simple question. If you had to summarize, let's say in a nutshell, what is the recommendation you would give to, let's say, transceiver architecture design for sub-terrace communication for those use cases? What would you recommend?
Since we in this study we just choose the fully digital beamforming architecture, but these studies can also redo for the hybrid beamforming. But in general, as the technology, as we go to the new technology, I think the digital part of the complexity will the power burn at the digital part of digital part will be scaled with the technology scaling. So probably the digital beamformings will gain a lot as the technology scaling, and by so it could be so before it is like I think this consume a lot of complexity, but it will gain this power will be reduced, and it will get benefit with the technology scaling, so it will become simple and good options as future. And the second suggestion is like we can try to offload our if we want to minimize our power spent at the head-mounted device side, then we can offload our powers to the access point. This, I think, is the two messages may help for the future system design for the VR system.
Okay, I see. Thank you.
Thanks.
So if there are no other comments or questions, I would like to thank Meng again for the nice presentation. And so according to the agenda, now we are having a break. I think we are in very good time. So we resume at 11 for the next presentation. So let's take a break, let's get a coffee, and we resume in 20 minutes from now. Thank you.